Or we can just ping pong back and forth. Hi, I'm Andrew Greenberg, adjunct faculty at Portland State University, local here. Thanks for coming to Portland. And this is Aaron Baker.
I'm an electrical engineering undergraduate at Portland State.
Can't spell geek without double E, so that's how cool we are. So we're going to give you a quick tour of some of the things we're doing here at Portland State University in open hardware and space. We're going to give you some background and maybe talk a little bit about some other open hardware stuff too. So here in Portland, we have a group of undergraduate and graduate students and local industry advisors and space nerds and open source hippies and everybody coming to PSU to build rockets and space stuff. And the question is, why at a university? Well, because labs are safe and they're predictable. And rockets can kill you in terribly weird ways, and it's interesting, and it's kind of stupidly hard, and you have to have MEs and EEs and CS people working together. It's a great interdisciplinary project. So let's build rockets. Our vision is to put a kilogram nanosatellite into orbit, right? So that's like a Coke can, basically, into orbit, right? And, you know, that's easy, right? So we said, what do you need to do that? And so that's, you know, the SpaceX Mars Colonial Transport and a Saturn V. That little white dot is a person. Yeah, we're not going to do that. We're going to instead run our slides. This is what we can do. This is an amateur rocket. And it's built by our friend Steve Jurgensen, and that's about what we are doing right now. So these are small, kind of hobby kit rockets. We've done 13 launches so far, but unfortunately, it's not anywhere near where we need to be if we actually want to put a kilogram nanosatellite into orbit. So that middle one, called the Lambda 4S, that's the world's smallest orbital rocket, and that's already like, I think it's like 30 meters tall, and that's us way down there on the left. So that looks hard, and in fact, it's really, 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 really hard, it turns out. So just to go some remedial orbital dynamics, if you go up, you come down, right? To go into orbit, you have to go up into space and then right. And this slide, sorry, left for you. And what that means is you're going around the world. You're literally falling around the world. Well, this is stupidly hard, because 10% of the energy is going up. 90% is that speed. It's 7.7 kilometers per second, right? How much is that? That means that your 1 kilogram Coke can destroy a city block if it hits it. That's how much energy you're putting into a kilogram. So it's even worse than that, though, and you guys understand this? It's not just the technology, it's the 10 to the $6 and the metric tons of lawyers we need to get to space. So, you know, it's not going to happen, right? It's even worse than that, because once you get to space, space is hard. There's vacuum, things outgas, there's temperature range. You've got 4 Kelvin space on one side and 1.3 kilowatts per meter squared on the other, so you're freezing and frying. There's only solar power. There's radiation in single event upset, so when something goes wrong, it's not like you can reboot the thing, right? It's got to reboot itself. You can't fix it when things go wrong. 30% of university rockets tend to fail. 50% of university-class satellites are dead on arrival on orbit. Everything is terrible because you have to have such good performance to get to space, and then once you get there, it's just awful, right? Let's do it anyway. And that is the open hardware ethos, and that's, I think, why we're here today, which is that the open hardware ethos is, this is too complicated and too hard, and let's do it all together anyway. So it's excitement in the face of overwhelming complexity, right? You guys deal with stuff that, you know, we have more complexity in an iPhone now than we had in all of the computational hardware of humanity in 1960, right? And so we're dealing with this on a day-to-day basis. Not typically done by amateurs. Nothing's been quite done, but hey, we've got duct tape now, so we can well, Kapton tape actually. We can duct tape our solutions together, and we can share. We can do a thing, and you guys can do a thing, and together we might actually have a system. And in fact, it's open hardware that makes it actually possible. Reference designs, stories, hey, this worked, you do this, you do that, and the idea of exploring the problem space of space, together, I think is really important. And then, you know, it's the right thing to do in democratization of technology, blah, blah, blah. Anyway, rockets.
Thank you, Andrew. We wanted to talk a little bit about our technical accomplishments also to prove that we can walk the walk and we're not just philosopher poets, though we're also that. Portland State Aerospace Society has been doing open everything since 1998. Open hardware, open software, open firmware, design documents, analysis. Our meeting notes are on GitHub, should you wish to read them, and I can't imagine why you would. Since 1998, we built our very first rocket. It was basically a hobby rocket kit flying something that's not even as sophisticated as an Arduino, but it was pretty cool for the time. We also flew an intermediate airframe that is just basically a better, more powerful, sophisticated version of the first hobby rocket kit. But we built our first truly engineered rocket starting in 2003, which flew what is basically a desktop Linux flight computer, an Intel Atom processor, and fun open source Easter egg. All of our software and hardware were published on Twiki, and we've had several migrations between different platforms, Twiki and IkiWiki and GitHub, and different ways of collaborating in an open space where we can share all of our documentation, all of our everything with everyone. This culminated in the most recent, which is an upgraded version of the original LV2 airframe, which has a bunch of really cool features, roll control system, aluminum fiberglass airframe, and basically, but we retired it last year, and we're moving on to bigger and better things. So the LV2 airframe had the most sophisticated version of this sweet beauty here, the LV2 avionics stack, which is about 10 years of legacy hardware. It includes the Intel Atom flight computer. It includes a Canard-based roll control system, which we sort of designed and it worked out of the box. It has a Wi-Fi-based communication system, which we've talked Wi-Fi to at Mach 1 using directional antennas and big fat power amplifiers and amateur radio licenses. And so it's a pretty cool system overall, although we're working on improving it. We have a couple of bragging rights we want to talk about. We think we're the first group ever to fly Linux on a rocket. We think we're the first group ever to fly talk Wi-Fi at Mach 1, and a bunch of other cool things. We flew solid state IMUs before they were cool because we have to get a hipster joke in because it's Portland. And we wanted to show you a little bit of, is this going to work?
Yeah, go to
Okay. We wanted to show you launch footage from our last launch, which this was from 2 years ago, this is our launch 2 years ago, with 60 frames a second camera. Some cool stuff you can see in the middle video. There's a black plastic enclosure hub sticking off the side of the rocket, which is a 3D printed umbilical disconnect, which we use to keep the rocket connected to electronics just until the very last second. Pretty neat and actually very simple design. Gonna fuzz up on me, I guess. But this rocket, like most of the LV2 launches, went about a little bit over Mach 1 and to an altitude of about 5 kilometers. Oh man. Talk about anticlimax. Yeah. There we go. All right. Well, it's loud and sounds intimidating. How do I get back into the...
Oh, that's funny. Oh, it's gone now.
Back into the slideshow.
There we go.
Oh, God.
Oh, sorry, guys.
One thing we desperately need is some business majors, just in case that wasn't obvious to everyone.
Where were you? There you go. Oh.
In the interest of time, we could just cut that.
Yeah, let's cut it out. Let me tell you a little bit about what we're doing right now. And again, everything you're seeing now is actually on GitHub, so you can go build your own LV2 class rocket with your own flight computers. So there's a cool thing that's going on. You need to go back to your communities and help out your local universities. There's a new space race. It's a university class space race, the first university to build a rocket to get to the Von Karman line, which is 100 kilometers. We're part of it. There's San Diego State University, there's USC, TU Delft University, lots of these guys working together to build the first amateur rocket to space, which is cool. Actually, not the first, that's the second. Someone's already done it, but no university yet. So what do you have to do? Well, exactly what you'd imagine, lightweight rockets. So we're switching to carbon fiber and Nomex honeycomb. And that's kind of an exciting thing for us working with new technologies. Our new airframe is 5 times better strength to weight ratio than the old aluminum one. We have a reaction control system so that we can guide the rocket in flight. This is a cold gas jet bottle with a 3D printed cold gas jets nozzles on the top. And of course, liquid fuel engine. This is a 3D printed, thank you i3D manufacturing, aluminum rocket engine. And it turns out though that the rocket engine is, by the way, LOX and liquid oxygen and isopropyl alcohol. It turns out that that's not really the hard part. It turns out that this is the hard part. You can make a combustion chamber, but then you need all this junk. You need data acquisition systems and valves, and you have to be safe. It turns out you can't kill undergraduate students even though they're free.
No slight to the mechanical engineers. Making a liquid motor enclosure is itself quite difficult.
Yeah. And you need the whole test setup to test the motor.
We're also working on an open hardware, open source satellite project called ORISAT. Thank you. Which we realized a couple years ago that our flight computer was basically a CubeSat, just not in a CubeSat form factor yet, and that we could turn our flight computer into something that was modular and that would either function as a satellite or function as a piece of hardware with a rocket as an Ethernet peripheral. So we're building ORISAT, which we hope will be Oregon's first satellite in actual space as an actual satellite. We're applying to a program called CSLI, the CubeSat Launch Initiative, which manifests educational CubeSats from groups around the country. They're trying to get one from every state and puts them on commercial missions and mostly takes them up to the ISS, and the technical term is hucks them off the ISS. And also will function as our rocket avionics system for the next 2 generations of the airframe. The primary mission is to not explode and to beep at us, sort of a Sputnik type thing. But as a secondary mission, our goal is to get real-time video downstreaming from space over our Wi-Fi communication system to a simple hand-pointed helical ground station that high school students will be able to build. It's partially 3D printed and then with a wire coil wrapped around it. We've tested this system so far at 125 kilometers, and we have good reason to think that it's going to work past that. This is a Cessna flight that was flying from Vancouver to north of the Dalles, and we got packets from all of those dots. We think we can push it up to 500 or 600 kilometers in a weather balloon launch that we're going to try in cooperation with PCC later this year, or next year. But eventually, that should be enough to get us to ISS orbit altitude, which is 400 kilometers. We're also using SatNogs, which there was a shout out to SatNogs earlier in another presentation that I can't remember right now, which is an open source satellite ground station, which is fully open source, open hardware. Satellite networked operational ground station. We're going to modify it and fork it and do our own thing, but build a fully functional ground station for our main ground station so we can do uplink to the satellite over multiple frequency bands. And finally, this is a project of particular interest to me, where we built an open source GPS receiver because GPS just stops working above certain speeds and certain altitudes. Now we have to take the antenna measurements that we get from that and actually do the digital signal processing to turn that into actual useful numbers that we can use in the flight computer. So that's a big SDR programming signal processing project that's going to happen in a capstone this year.
So there's a lot of other open hardware space projects, and you should all go out and instantly join them and help them so that we can use that stuff because space is hard. So the open source satellite initiative is actually now old. You talked about SatNogs. UpSat is now possibly the very first completely open CubeSat. Ours will hopefully be the second, I guess. LibreCube, I don't know when they're going to fly, but they are a big ESA-based open CubeSat. There's Open Rocket, there's Altus Metrum, there's Mach 30 Foundation. All these people are working on open space or open rocket kinds of things. It's really cool. It's all kind of coming together. We do have a slide of shame. Sorry, University of North Dakota. A lot of people, and you guys, I was really, really pleased to see when they said, is the Raspberry Pi open source? Nobody raised their hands. Thank you so much. The Open Orbiter is open except for the fact that it's not, and there's lots of these people who say they're open source when you talk to them at space conferences, and the reality is they've literally not published any of their CAD or any of their software or anything. And so we're really sensitive to that because everything we have is published.
One last thing. We need your help. We weren't joking about the $10 to the $6 thing, so if you have some cash to throw around, that we do a Kickstarter every year, a crowdfunding campaign every year. But more than that, we desperately need your experience, your expertise. We have tons of community volunteers and tons of community mentors. Both of our big ongoing projects right now are very difficult. We need you steely-eyed rocket nerds. So you can go to these URLs, psas.pdx.edu or orisat.org to get interested in either of those projects. Our next launch is in spring 2017. We're launching the carbon fiber airframe with the reaction control system and some of the other hardware we've built recently. And I'll leave this info slide up in case any of you are interested in getting in touch with us. Come to our meetings at PSU. Come help out. You've been great. Thank you very much.